This is the Chapter 5 practice test walkthrough. Number 1. The number of waves that pass through a given point in space in 1 second is called the frequency. Answer choice C. Frequency is the number of waves per second. Wavelength is the distance between two waves. Photon is a particle of light, and a quantum is a unit of energy. So frequency is the number of waves per second. In the diagram here, question 2, which diagram shows a wave with the shortest wavelength? So like we just said, wavelength is the distance between points on two consecutive waves. So you're looking for the waves that are the shortest, that are the closest together, which in this case is going to be D. And question 3, which diagram shows a wave with the lowest frequency? Lowest frequency means the fewest number of waves per second, and if we are assuming these all travel at the same speed, you could also say that the one with the lowest frequency is also the one with the longest wavelength, which is going to be B, because the longer waves are going to take a longer time to get through that imaginary point in space. So they're going to have a lower frequency. According to the Bohr atomic model, atoms in which all electrons occupy the lowest energy orbital are said to be in an excited state? No, that's when electrons are above the lowest level. Solid state, that has nothing to do with Bohr's model. Agitated state is just another word for excited. The ground state, when all the electrons are on the ground floor, the lowest level, that is the ground state of an atom, according to the Bohr model. The regions of space in which an electron is likely to be 90% of the time are called atomic orbitals. Those are the regions in space where we think the electron will be most of the time. Not all the time, but most of the time. Electron clouds are something we haven't talked about yet. Principal energy levels are the main energy levels. They're not orbitals. And the valence shell is just the outermost orbitals. So the answer is A, atomic orbitals. Using the diagram below, which is the electromagnetic radiation described as having a frequency of 7.5 times 10 to the 16th. Well, if we look down here, this bottom row of numbers beneath the diagram of the wave represents the frequencies over here. So we want to look for a frequency with 10 to the 16th. Well, there's some here and some here. Since this is 7.5 times 10 to the 16th, it's in between 10 to the 16th and 10 to the 17th, which makes it in the ultraviolet UV range. Electromagnetic radiation with a wavelength of 3.9 times 10 to the negative 9th meters. If we look along the chart here, the wavelengths are on the top. Negative 9 falls between negative 8 and negative 11, which would put this in the range of X-rays. What is the frequency of light with a wavelength of 6.51 times 10 to the negative 9th meters? Well, here's the formula for speed of light, wavelength, and frequency. And to find the frequency, we take the speed of light divided by the wavelength. So in this case, we have 3.00 times 10 to the 8th meters per second divided by 6.51 times 10 to the negative 9th meters. So with three significant figures, that comes out to 4.61 times 10 to the 16th hertz, or waves per second. What is the wavelength of light with a frequency of 2.40 times 10 to the 14th hertz? Well, we're going to use a similar setup for finding the wavelength. The wavelength is the speed of light divided by the frequency. So 3.00 times 10 to the 8th meters per second is the speed of light. The frequency we're given is 2.40 times 10 to the 14th hertz, waves per second. And that comes out to 1.25 times 10 to the negative 6th meters. What is the frequency of light with a wavelength of 3.19 times 10 to the negative 8th meters? Again, to find the frequency, you need to take the speed of light and divide it by the wavelength. So 3.00 times 10 to the 8th meters per second divided by the wavelength given is 3.19 times 10 to the negative 8th meters. So that gives you 9.40 times 10 to the 15th hertz. What is the electron configuration for phosphorus? So the first thing we need to know is how many electrons does phosphorus have? So if we look on the periodic table, phosphorus is right here. Okay, it is number 15, so it has 15 electrons. Alright, so we need 15 electrons, and we need to use this Aufbau sequence that tells us what order the orbitals fill up in. This sequence of energy levels and sublevels will not be given to you on the test. Make sure you have it on your note card. You will be given a periodic table, similar to this one, but you will not be given this sequence, so make sure you either memorize it or have it written down. So, to fill in the orbitals, we start with 1s, which can hold 2 electrons. And then the next is 2s, which can hold 2 electrons, followed by 2p, can hold up to 6 electrons, that gets us up to 10. Next would be 3s with 2 electrons, we're at 12. The next sublevel is 3p, and I need 3 more electrons, which will all fit there. So 2 plus 2 plus 6 is 10, plus 2 and 3 is 5, so that's 15 electrons. And I've done it in the correct order according to the sequence up here. So 1s2, 2s2, 2p6, 3s2, 3p3 is the configuration for phosphorus. The configuration for fluorine. Again, find fluorine on the periodic table. Its symbol is F. It has 9 electrons. So, using the sequence again to fill up 9 electrons. 1s, 2. 2s is next. That can hold 2. 2p can hold up to 6, but I don't need 6. I only need 5 more because I've got 2 and 4 in the first 2 s levels, plus 5 gives me 9 electrons. Okay, so that's the configuration for fluorine. Now we're going to be working on the noble gas configuration for Tc, which is technetium. And to find technetium, you have to look for the symbol Tc on this periodic table. The periodic table you'll have will have the names on them as well, so you don't need to rely on just the symbols. So it's element number 43. We need to know that, 43 electrons, but we also need to know which noble gas to use in the configuration. And remember, the trick to this is when you look on the periodic table, find the element that you're looking for. Technetium is here. You're going to go up 1 row all the way to the right. That last element is the noble gas that we're going to use, so it's krypton. So 43 electrons, our noble gas is krypton. And then in order to determine what's going to come after those brackets, we look at the row that technetium is in. It's in the 5th row. So after krypton is going to come 5s. So I'm going to transfer this over to the next slide. So we know we have 43 electrons. We know our noble gas is krypton. And we know that the next sublevel that comes after krypton is 5s. Okay, and 5s2. Now you need to figure out how many more electrons do you need. The next sublevel in the sequence is 4d. 4d can hold up to 10 electrons. How many do I need? Well, krypton is element number 36, and I need to get from 36 to 43. So 36 here plus the 2 from 5s means I'm at 38, so I only need 5 more electrons to get to 43. Okay, 36 plus 2 plus 5 equals 43 electrons. So that's the right number. This is the noble gas configuration. Krypton, 5s2, 4d5. Okay, the noble gas configuration for iodine. Iodine is the letter I, which is down here. It's element number 53. And we're going to go up 1 row, and we just have to go over 1 block. We're going to use krypton again as our noble gas, which means iodine is in the 5th row. 5s comes next, and we need to get from 36 for krypton up to 53 electrons for iodine. So 53 electrons, starting with krypton, which has 36 electrons. The next element is 5, or the next sublevel is 5s. After 5s comes 4d. So 5s can hold 2. 4d can hold 10. So that gets me to 48. And then 5p. So we've done 5s, 4d, 5p is next. And I'm at 48. I only need 5 more to get to 53. So it's 5p5. So that equals 53 electrons. Krypton, 5s2, 4d10, 5p5. Okay, this time we're going to be doing the orbital diagram for the element copper. Okay, copper is symbol Cu. It's element number 29. The orbital diagram uses the same sequence, but instead of just numbers and letters, we're going to be using the boxes and arrows. So we're doing copper, which is element number 29. 1s, 2s, 2p has 3 orbitals, and then 3s, 3p, 4s, 3d. Okay, so we're going to fill these up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Need 9 more. 21, 22, 23, 24, 25, 26, 27, 28, 29. I don't need to fill in that last box because I've already got my 29 electrons. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d9 gets me 29 electrons. So you need to know that antimony has the symbol Sb. It's element number 51. And we're going to do a noble gas orbital diagram. So it's going to be the boxes and the arrows, but we're going to use the noble gas shortcut that we just used in the electron configurations. So I need to find the noble gas to use, which is up 1 and over, gets me to krypton again. And krypton is going to be in brackets. And remember that krypton equals the first 36 electrons. So after the brackets, I'm going to go to 5s. So to do the noble gas orbital diagram, we're going to start the same way we did in the noble gas notation, which is with the element krypton in brackets. And remember, that's number 36. We're trying to get to element 51, not to be confused with area 51. And we're going to start after krypton with 5s, and we're going to put the box with 1, 2 electrons, so that's another 2, followed by 4d, which is the big one with 5 boxes. 1, 2, 3, 4, 5 boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now I'm up to 36 plus 2 plus 10. That's 48. And the next orbital in the sequence is 5p, which has 3 boxes. I only need 3 more electrons, so I'm going to split those up into the 3 boxes. So 5s2, 4d10, 5p3, and there's 36 plus 2 plus 10 is 48 plus 3 equals 51. So I have the right number of electrons. All right, finally we're going to do again a noble gas orbital diagram, this time for platinum, Pt, which is element number 78. And we're going to use a different noble gas this time. Up 1 and all the way over gets us to xenon. So xenon is element Xe, and it's number 54. So to do the noble gas orbital diagram for platinum, we're going to need a lot of room here. We're trying to get to 78 electrons. We're starting with xenon, okay, which is element number 54. The next thing in the sequence, if you look at platinum, it's in the 6th row, so it's going to be 6s with 2 electrons. Look up here, after 6s, the next sublevel is 4f. And remember, f has 14, can hold 14 electrons. It has 1, 2, 3, 4, 5, 6, 7 boxes. And we're going to fill those all up. Okay, 2, 4, 6, 8, 10, 12, 14. So I've got 54 plus 2 is 56, plus 14, that gets me to 70. The next level in the sequence is 5D, so this is going to be 1, 2, 3, 4, 5 boxes. So I'm up to 54, I'm up to 70, so I need 8 more. 1, 2, 3, 4, 5, 6, 7, 8. So the last 2 boxes only have 1 electron each. That gets me to 78 electrons. Okay, identify each of the elements described below. So the easiest way to do this is to count up the number of electrons, which is the total of the little superscripts, the little exponents. So 2 plus 2 plus 6 is 10. Plus 2 plus 2 plus 6 is 20. So up to here gives me 20. 29 would be here. Element number 29 on the periodic table is Cu, copper. So that's the configuration for copper. Now we've got argon in noble gas brackets, which means that starts at number 18. So 18 plus 2 is 20, plus 10 is 30, plus 2 is 32. So if we look for element number 32, that would be germanium. Ge is germanium, discovered in Iceland. And the last one, radon, is way down here in the corner. It's element number 86. Radon is 86, plus 2 is 88, plus 14 is 102, plus 3 is 105. Element number 105 is dubnium, DJ's favorite element. All right, oldies but goodies. In an experiment, some batteries are placed in 3 different refrigeration units set at temperatures of 15, 5, and 0 degrees Celsius. The size of the batteries and timed refrigeration units are kept constant. After 3 weeks, the batteries are placed in flashlights, and the time required to drain the batteries was measured. What is the independent variable? Well, the independent variable is the thing that is different each time that is changed on purpose. The thing that was different for each of the batteries, since the size of the batteries and the time in the refrigerator is the same, the thing that changes each time is the temperature. That's the deliberately altered factor in each of the trials. The dependent variable is the thing you measure in response to changes to the independent variable. And what is measured, it says right here, the time required to drain the batteries was measured. So I'm just going to call that the battery life. How many protons, neutrons, and electrons does the atom 8035Br, that's bromine, have? Well, you need to remember, first of all, you could do this one of 2 ways. You could look up bromine on the periodic table and see that it's atomic number 35. Or you could remember that the number on the bottom is the atomic number, which is also the number of protons. And since this is a neutral atom, 35 protons means you've got to have 35 electrons to cancel them out. And the number of neutrons is the mass number, which is the number on top, minus the number on the bottom, which is the number of protons. So 80 minus 35 is 45. So there are 45 neutrons in that atom. Calculate the following to the correct number of significant digits. So when you do this out on your calculator, you get 3.77, which has 3 significant figures, 1, 2, 3. And you have to round your answer when we're multiplying and dividing to the same number of significant figures as the starting number, which one of these 2 numbers has the smaller number of significant figures.